Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The second session here is, the theme of it is tools and technologies for communication and problem solving. And so that will be more of the emphasis for this. And our first speaker in this session is Curtis Wong. And Curtis is a principal researcher in the eScience group at Microsoft Research. He joined Microsoft in 1998 to start the Next Media Research Group, focusing on interaction, media, and visualization technologies. He has been granted more than 25 patents in areas such as interactive television, media browsing, visualization, search, and gaming. He's the co-author of Microsoft's 5,000th patent in 2006, 10,000th patent in 2009. He's the co-creator of the Worldwide Telescope, featuring the largest collection of the highest resolution ground and space-based imagery ever assembled into a single learning environment, inspiring millions to explore and expand the universe. His most recent project is Project Tuva, featuring the 1964 Messenger Series lectures of Nobel Prize-winning physicist Richard Feynman, whom many of us in the Department of Energy knew, which are an interactive research media player featuring rich interactive simulations and related content. His presentation this morning is called Telling Stories in the Cloud. So help me welcome Curtis Wong.
Thank you. Okay, well, I'm really excited to be here with you guys. You're sort of my people. Multimedia, interactive, visualization. How many people here have heard of the Worldwide Telescope? Can I see some hands? A few, maybe almost half. How many people have played with it? About a quarter. Anybody authored with it yet? Oh, you have a real treat coming for you. Okay, so I'm going to spend a little bit of time talking a little about the Worldwide Telescope and take you into stuff that you probably haven't seen or noticed before. And then more of the recent work we've been doing with it is bringing in data, and I'll show you an example of that. And then there's also been some really interesting work, I think, around what we call guided tours, which are essentially like hypermedia publications. It's very similar to the last speaker, and I think you'll find that particularly interesting as well. So let me just dive in here. I'm going to set up running here, and I'm going to turn this down. Excuse me a second here. It's amazing. It just happens. Okay, so Worldwide Telescope will run at pretty much any resolution. Right now we're running it at a fairly low resolution so that it can be captured on video. But when we're running it on like a wall or something like that, we can pretty much run it at any resolution, which is pretty wonderful. So you're looking at the visible light view of the night sky. This is the Milky Way, of course. And this is a trillion pixel image. It was put together with some folks here and based on the Palomar DSS survey, which is about 1,700 plates. And those were mosaic together, and stitches were eliminated, and so you can do this kind of thing, zoom in pretty much anywhere. But within this same environment, we have the ability to compare other wavelengths, and you notice that they're all sort of registered. So if we take a look at, say, the X-ray view, you can zoom in and look at this heat signature from a supernova remnant, and we can make that a foreground view, and then we'll go over and make the visible light a background view, and you can compare two different data sets. So you can see the heat signature as opposed to the debris clouds from that particular supernova remnant, or if you went and wanted to see that in hydrogen, you can see the compression of hydrogen from that particular explosion. So having base layer imagery is particularly important. We have 50 of those, 50 different wavelengths, and then within collections, we have collections from the Spitzer, Hubble, Chandra, all the highest resolution imagery of all of them here, and these are overlaid on top of the visible light view that you have. Say, here's an example of M42, and notice down below, we're showing you as we slew over this blue rectangle. It shows you the field of view as we're zooming in to show you what portion of the sky you're looking at. These numbers here tell you the field of view in degrees, and down here it shows you what part of the celestial sphere you're looking at. So you're looking at a very high resolution image of M42, and you can sort of zoom down as far as you want. This happens to be a proplet that has evolved into a disk of dusk where you can see the star forming at the center here, and there are many examples here in this particular area. Here's another one, and an earlier stage proplet right there. So let me show you something else. One of the most exciting features, I think, of Worldwide Telescope lies in this idea of what we're calling guided tours for the public, but essentially they're just paths within this very, very large data set of hundreds of terabytes of imagery that we have. And what's exciting about it is that it allows you, because we have built in an authoring environment, to create these paths that you can richly annotate with graphics, text, imagery, hyperlinks to other things as well. I'll show you an example of, this is a tour that Alyssa Goodman did a couple of years ago. It's interesting that when you add up all the people that have seen this tour, and then you compare it to all the people that have been students of hers, freshmen and undergraduate, all the people who have read her technical papers, all the people that have been in public talks, it's about a factor of 10 more have seen this tour. So in terms of public outreach, it's a terrific opportunity to, let's see, is that right? Let's see. We have a small technical problem. It's not coming through because it's still coming through on my speakers, which is... There we go. One of those things.
Galaxies are first, and we see that because we're inside it. Here's a spiral galaxy not far from us, about 12 million light years away, called M81. If we look at it in optical light, we see billions of stars shining together in a spiral pattern. If we look at the heat from M81 rather than the light, it looks like the false color orangey image we see here. This Spitzer Space Telescope image uses long wavelength cameras that can see heat, just like the one that took the picture of this cat. Galaxies are filled with tiny particles called dust that absorb the light from stars.
So it feels like video. Video is like the most powerful media form we have. It can really sort of engage somebody at a deep level. But the problem with video is that if it's something that you already know about, it's not going fast enough. If it's something you don't know about, it's going too slow. So the opportunity really here is that, as I mentioned before, these things that look like video are just rendered video in real time. And so because I've paused, I'm back in this environment of the Worldwide Telescope, so I can then look at a particular object from any other telescope. I can look at a different part of that particular object that I was looking at. I can look at other tours that intersect with this particular galaxy, so I can sort of semantically branch off. If I wanted to know more information about this particular galaxy, I could go and look up, if I was a kid doing research, I could go look at Wikipedia and go get some information from Wikipedia. So, that's one source. There's other sources. If I was an astronomer and wanted to know what's the latest papers that have been written that reference this particular object, we can go and it does a real-time query to Smithsonian ADS, and it'll show you all the results from that, of which there are 2,625, and the most recent one was from January of this month. And there are other information sources that are essentially on the web. But if I wanted to get an original source image, I could directly go get a DSS image from that source or somewhere else. Or if I wanted to get an image from the Sloan Digital Sky Survey, it goes and does a query, pulls it out from the database, and I don't have to do anything other than just access it. And then there's a number of other things you can do with it. So far we have this rich visual environment. We have the ability to create these paths in this environment. And then we also have this connection to data underneath it. And so that gets particularly interesting from an educational perspective as you start to think about, well, what kind of stories can I tell about these different environments that we have? And we have quite a lot of different environments in here. I mean, if you look at planets, you can create, here's the planet Mars, and if I wanted to sort of explore down into a particular area of Valles Marineris, you could do it, and I could create a path down into the valley, and I can annotate it based on interesting things that I was looking at or seeing. And that's one example. Of course, we have the entire virtual Earth data set as well, whether it's, I'll show you here. Whether it happens to be the straight Earth view or the map view or Earth at night, or these are blue marble, winter and summer. And these can all sort of be used within that experience. If I wanted to go out beyond the solar system. So right now we're looking at the sun and planets, actually quite small. I can turn on the orbits, but when I show you the orbits, you'll see that we have quite a lot of bodies here. Okay, see the little lint balls? Those are the moons around. As we look at Jupiter right here, you can go in and see all those. We can crank up the clock and you see them spin around like crazy. But let's go get some other context for kids. You can see why Pluto is not a planet. It's sort of an acquired object. But let's take a look at Orion here, the little 3 stars in the belt. If you keep going further out, you notice that the constellation starts to distort. Of course, that's because the planets in Orion are at different locations. I mean, the stars that are in Orion are at different locations. But we can exit, the Milky Way and continue going out into the million or so galaxies in the Sloan. So if you look at some of these galaxies here, such as this is the Coma cluster, each one of these has a real galaxy behind it, and you can go and say, I want to get information about that particular outlier galaxy. Here's the image of that galaxy. There's the spectra. There's the redshift. You can download the data for it. You can take a look at chemical composition, and this is sort of information that's behind every one of these million galaxies that are here rendered. So let's go back to the Earth, and I'll show you a little bit of what we can do with data. Okay, so the first thing I'm going to do is I'm going to go find some data, and this one will be useful. I say this one. So I have some data in here in Excel. A lot of people have data in Excel. So this one happens to be earthquakes from 2009 to 18 months later, 2010. It's about 40,000 rows of data, and it's difficult to sort of discern any real insight by looking at all of this data. But we've been working on connecting Worldwide Telescope with things like Excel. And so we can go and take that data and bring it into Worldwide Telescope. So let's see what's going on here. Let me copy this and bring it into here. All right, so, and here we have, I'm going to minimize this. Let's take a look at, so here's all of that data in Worldwide Telescope, and we can play with some of the properties of this. If we wanted to change the scale of some of the data that we were looking at, you could see it here. Magnitude. Oh, okay, wait a minute. The challenge I have right here is that I didn't select a critical field, which is magnitude. That's why it's not plotting anything. All right, let's try that again. All right, I'm going to delete this guy out of here. And let's create a new layer. All right, that's better. So it's pretty easy to sort of see the ring of fire. We can change the scale of that so that's a little bit. That way it'll allow you to look a little bit deeper at what we're seeing there. We can change the color of it as well, make it a little bit more dramatic. But when you start looking at these earthquakes, you notice that there's some funny patterns of these quakes out in the middle of the ocean. And you kind of wonder what's going on out here. And so what we can do is we can switch to a different view of the underlying information about the ocean floor. And you can see that, of course, this is a little bit of a subduction zone where you see the pattern of the earthquakes following that subduction zone there. You can go look down here. Here's the Haiti earthquake. And it was very close to the surface. But, you know, this is an interesting distribution right here, right above Puerto Rico. Seeing some interesting structures here. We can take this same data and look at it over time. So we'll select that, select time series, and we can go into the clock and crank up the clock a little bit more. And pause there. So you can start to see some of these patterns here. Let's go into here and see them a little more closely. Some of them even look like lightning bolts. Let's speed this up a little bit. I think what will help us too is if we adjust the latency of it to give it a little bit more persistence, so we can look at more temporal patterns. So we're seeing something here that is very difficult to see any other way. And one of the nice things we have about this environment of being able to author in this space, I'm going to pause here for a second, is that we can create an annotation about the data here. So we're going to create a little guided tour. And the way you create a tour is just by deciding on a point of view, which happens to be this one. We could pick a different one. And it creates a little snapshot of a point that we were looking at. And then maybe what we might want to do is look at it from a little different angle. And it'll interpolate between those two views. And we also want to pick a segment of time that we're looking at. Say that segment. And then if we set an end camera there, and then we can create another slide, that will be a starting point, and then we'll move the time slider a little bit more. We might change the view a little bit more here. Add an in camera position to that, and then we can take a look at what we have. So I just saw something interesting in here. Maybe what I wanted to do is I might want to call something out, and maybe I wanted to add something here of, let's see. I want to make a little audio note to somebody to take a look at that thing. And let's sort of preview that.
Tom, can you take a look at these temporal patterns? I think there's something interesting going on.
I just recorded that with a little digital audio recorder. And then, you know, you can, within this space, you can add anything like text, image, pictures, and all of those objects. If I added, say, even something, well, even this thing, if this ring, I wanted to do something to it, if I wanted to hyperlink that thing to a website, I could go to the ISTE website and get that URL, copy that, paste it into here. And I'm actually going to mute myself because I don't want to hear myself again. But So that's going, and I could click that and would link me to some relevant other related piece of information to what we were looking at. And I could actually animate this particular object just by setting a different starting and ending point in between those two. So that's sort of a simple example of something that we're doing around data. I'm going to show you a guided tour that was created by some astronomers at the Harvard Center for Astrophysics. And this one is called John Huckrow's Universe, as a dedication to John Huckrow, who is one of the two astronomers that worked on the original work on the large-scale structure of the universe.
14 billion years after the Big Bang. It's only during the last 100 of that 14 billion years that human beings have figured out that we live in an expanding universe. When John was born, no one really knew how fast the universe was expanding, how old it was, or where the galaxies were in that stretching space.
So this tour is 12 minutes long, so I inserted these
Lucky
little
for us, John
logos of
Huckrow
yours
saw
in there
our ignorance as a fantastic
so we can sort of jump through it, and I can show you some different features about this. Now, what we're doing here in the background, this is actually a path within the Sloan Digital Sky Survey, which is sort of a testament to him. So this is an example about the analogy
Here's
of
a three-dimensional view of the top of Mount Hopkins in Arizona, the site of many of John Huckrow's astronomical observations. Adding altitude measurements to a two-dimensional map of this part of Arizona gives a 3D view. In the same way, adding distances inferred from galaxy redshifts to a two-dimensional map of the sky can make a three-dimensional map of the universe. 533, seen here. One study of Markarian galaxies got John into a heated discussion in the journal Nature about whether the distribution of these galaxies was lumpy or smooth, another harbinger of things to come. After his PhD, John moved east to the Harvard-Smithsonian Center for Astrophysics. He never left. John and a number of his young colleagues were deeply influenced by Jim Peebles' desire to understand the origins of large-scale structure in the universe. Big surveys of galaxies seemed the right way to proceed, and John was up for the challenge. If you measure a galaxy's redshift, you can infer its distance. This lets you add a third dimension to maps of the sky. On the Earth, adding altitude lets you understand mountains and canyons. Would a 3D map of the universe similarly reveal such grand structures? Soon after his arrival in Cambridge, Massachusetts in 1976, who wondered whether the universe was smooth or lumpy. At that time, many people had opinions, but there were few facts. To build a 3D view of the way galaxies are arranged in space, you need a spectrum for hundreds, or more likely thousands, of galaxies in order to determine each one's redshift and thus its distance. And no one had ever set out to measure and summarizes some big redshift surveys.
It's an interactive timeline.
The CFA-1 was the first systematic attempt to map out a large swath of the universe in 3D. In the late 1970s and early 80s, John and his colleagues spent hundreds of hours atop Mount Hopkins measuring hundreds and seemed to indicate a 1,000,000 cubic megaparsec hole in the galaxy distribution. But nobody knew if voids like this were rare or common. The results from CFA-1, published in 1982, hinted that there might be interesting large-scale structure in the universe, but they were not conclusive. A larger survey with more redshifts was needed. After CFA-1,
so this is the actual CFA survey plotted against the sky, each one of these little squares is that survey. In fact, you can go in and look and find a galaxy behind each one of those little squares.
Structure in the universe, but they were not conclusive. A larger survey, 2 redshift survey, should employ a different strategy than CFA-1. She thought that more would be learned by sampling long, thin strips on the sky than by samples over a broader region, as had been done in CFA-1. The terrestrial analogy is that more can be learned about the Earth's general topography from a long, thin strip of elevation measurements stretching from coast to coast than from sampling elevations over a random patch of Earth. After all, the CFA mappers reasoned, a long strip would encounter rivers and mountain ranges and oceans, while a sampled patch could turn out to be all ocean or all Iowa. John, Margaret, and their students and co-workers began the CFA-2 redshift survey in 1984, using the long, thin strip strategy that Margaret had proposed. The first strip was 130 degrees long and just 6 degrees wide, and contained the 1100 galaxies highlighted here. A new insight was their 3D map.
So you
They
remember
looked
this.
at a view of their first slice, seeing as if they could look at the universe from above. Here is the famous first slice from CFA2, where velocity, a proxy for distance in a Hubble flow, increases radially outward. The range from east to west, stretching for 130 out of 360 degrees around on the sky, is shown as the angular coordinate from right to left. The thin range of 6 degrees north and south is scrunched down in this diagram, which shows galaxies of the slice projected to make a two-dimensional view, as if we viewed the universe from an orientation 90 degrees away from our usual sky view. It's easier to understand this diagram if we look at it in context, so let's put it there before we dissect its meaning. Shown here again are the galaxies in the first strip as projected on the sky in 2 dimensions. If we color code the same first strip galaxies in a 3D view of the universe given to us by the modern Sloan Digital Sky Survey, we can see how a strip on the sky translates to a wedge in 3 dimensions. In John's modest description of the first slice, he says, the total for CFA2 reached
So this is
about
18,000 galaxies
in the
plotted
1990s.
against the sky.
Here we show all 18,000 galaxies on the sky, color-coded by their redshift.
So I can pause and you can sort of see that segment of the strip that they're talking about. And you can drill into any one of these. And the color code tells you about the redshift. We can go and pull up redshifts about any one of those.
The total for CFA2 reached about 18,000 in the 1990s. Here we show all 18,000 galaxies on the sky, color-coded by their redshift. Red markers are farthest, and blue nearest. The results from the CFA2 redshift survey are best understood in 3 dimensions. Here we see the 3-dimensional locations of the same 18,000 galaxies we saw just a moment ago on the sky. The bubbles and sheets are now obvious, as is the Great Wall. The CFA redshift survey inspired many larger surveys. The Sloan Digital Sky Survey is shown here. The Sloan survey measured redshifts for hundreds of thousands of galaxies. The Cosmos synthetic 3D map of the Sloan galaxies, shown here in Worldwide Telescope, was created by placing 2-dimensional images of galaxies at the right positions in 3-dimensional space. The CFA survey, where each of the 18,000 galaxies is marked by a colored dot, was much smaller than the Sloan. But the essential features of large-scale structure, a network of filaments and
Okay, I want to make sure we have time for questions. So, as you know, this, like all the others, it's a real 3D model. There's real data behind all of those points. And I think it alludes to a little bit about the last speaker in terms of how you might connect both visualization and the data underneath it. Worldwide Telescope connects to a number of different data sources transparently within this application. You don't know that, some of the Mars data is coming from JPL and other data is coming from other sources, and you don't really have to care. All you just have to say, point me to the data, and you can get it. And that was part of the original reason for wanting to build Worldwide Telescope, because many of the astronomical imagery, say for the Hubble, was resident Hubble visible light. Then the X-ray stuff was at Chandra, and the infrared stuff was at Spitzer, and all these different labs sort of had their own sort of data. And there was an effort about 10 years ago to try and bring all of this imagery into something called the International Virtual Observatory Association. And part of that was just to have a standard so everybody could publish their data on the web and we could sort of get to it. And so I pushed them about 6 or 7 years ago in saying we should create this Uber environment where everything is brought together seamlessly and then connect it with these abilities to author experiences as well as connect them with information. And now the IVOA essentially uses Worldwide Telescope as their de facto visualization tool. So we have a few minutes. I want to make sure we have time for questions. So.
Gary?
Yeah, thank you. I think this is it's a great demonstration of that kind of data linkage and such. I had a question just in terms of whether you knew how people were using the data yet. A number of the examples you showed were probably more educational,
Right.
which is probably good
Right.
for a more lay audience like we have
Sure.
here. Do you know, are scientists using this as a way to get access to data sets, to,
Well, as
to
a way to
archive
publish
their
their
data
data
sets
sets.
and so forth?
Yeah, I mean, I can show you an example. Let me bring up, here's a data set. There's an astronomer that did that tour about dust, and her data set. She's posted her data sets, and if I click here, so this is her data set overlaid on top of Worldwide Telescope, and I think that's the real benefit of it, is they have their data sets, and they can compare their data to any other multispectral data from a number of different sources. And we have an API so that they can just construct their own unique viewer on a web page that they can do their own things with. There's a connection for amateur astronomers. They can take a picture of the sky, whatever it is, upload it to Flickr, and at Flickr there's a group called astrometry.net, which solves the position of the stars, and then if there's a link to Worldwide Telescope, and they can see their image overlaid in Worldwide Telescope, and you can sort of crossfade between to look for, what you can see in their image versus what's commercially available. Another question?
Yeah, I'm just curious about the project size in terms of how many developers have been working on this, how long have you been working on it, those kind of pieces of information.
Well, I've been thinking about this project for about 30 years, and there really was not the technology to do it until Jim Gray and Alex L.A. started working with the Sloan about 10 years ago. I joined them. I did a little bit of work with them in 2002, and that was when I said, just having the data is enough. We should build this larger thing, and they were huge supporters of it. And because it was one of these, I wasn't in the eScience part of the organization at that time, and so it wasn't really sort of core in my job, so it sort of was this background thing. And about 2006, I had a little window of time that I could start working on this, so I hired a really good developer named Jonathan Fay, and Jonathan and I worked on it for about a year and a half. We got an intern to help us with all the data, and that was the first launch we did in 2008. We had a number of other people help us with the website and things like that, but the core team was very, very small, just because it's kind of a labor of love. We wanted to create something for education and something that we hope would have some benefits to science, and I think some of the data visualization work that we're doing now, I think, has a lot of interesting potential, both scientific and commercial. So.
Hi, this is a really compelling demo, and actually some of the features here remind me somewhat of the work on collaborative visualization by Jeff Hare, who's at Stanford. In particular, some of you may know about his census project. And one of the nice things there is that the system kind of directly supports communication and discussions and collaborations based on the data set, kind of anchored with respect to the data set. Mm-hmm. It seems like this system would definitely support this type of discussion as well. Are there features built in, like for commenting and for kind of having discussions around these different views of the data?
We haven't done that yet, but I mean, as you saw, Alyssa has a data set that I was just showing you. She could easily make a tour with that data set, which has pointers to the data, and that can be shared with someone else. She can annotate it and send it to somebody else, and it's a very small file because it's basically XML with pointers, and then somebody else can annotate it too, or send it to a group, or have it just be more largely available. So there is a mechanism for it, and it's another one of our sort of mini to-do things.
I mean, it seems like it just would be so cool to have that video that's been viewed by so many people, for instance, and then having them be able to leave particular kind of comments or notes kind of embedded as part of that guided experience.
And have it as a space where you could sort of view all this sort of discussion and collaboration sort of geographically, look at a heat map of the whole sky and say, where's the activity and where's there not the activity, and should there be? And, Harvard is working with ADS, which is the publication sort of home for all those papers that I was showing you, to generate a heat map of publications about the sky. Because wouldn't it be great to try and figure out, where's all the scholarship going and where is it not, and what are we missing in an interactive way? So.
Let me get this right back here in the back, Peter, and I'll come up to you in a second.
kind of related to that, this seems like a new way to, or a different way than the traditional method for browsing and navigating data. So have you found that this has resulted in a different type of metadata structure or for semantics, so that in support of this way to kind of be tying things through geographic location?
Oh, a different kind of metadata structure. Well, we were trying to use sort of conventions that exist out there already, which allows us to bring in lots of other metadata without having to do anything special. So we can bring in shape files, we can bring in 3D studio, polygons, we can bring in a whole number of different things with this environment, and each sort of you can define each one as a separate layer, which has its own rendering space, which you could then plot your data into that rendering space within the larger context of another environment. So,
it seems like with that component where you're looking at this space and let's go look at, you're kind of querying what's out there. I didn't know if maybe having that kind of link is going to require anything different, or anything that you found?
Well, for the sky and the earth, there are existing sort of conventions there. We're also working on, totally abstract 3D or ND spaces that you can do visualization, and we're, going to try and do the same thing there, where we use the same convention, because we don't want to invent too many things that we don't have to.
Two things. First, I want to note for the audience that when the astronomer started talking, the clock at the back stopped.
I'm sorry, what? I didn't hear that.
When you started talking, the clock at the back stopped.
Oh.
What I'm interested in, I know it's tough for someone who's been so involved in this, is the Whole Earth Telescope at a disruptive technology stage for astronomers? And if it is, are they afraid of it or welcoming it?
It's really interesting, because I think in the early stages, a number of astronomers said, well, that's really cool. It's for education, right? You know how that argument is. And then some of the astronomers that were using it were showing some other astronomers saying, well, I could do that, but let me show you how I do it here. And it's like a fraction of the work. And so what would you rather be doing, being a computer programmer or doing science? And they go, you're right. I mean, some of the early advocates of Worldwide Telescope to this day too, are two astronomers at Space Telescope. Ironically, those two astronomers are the ones that persuaded Google to do Google Sky. But no, I think they're partly a fan of what we've been doing, because we've sort of taken it much further. I mean, we were very passionate about the accuracy of rendering. So when you're doing the sky, you can't do the sky in a Mercator projection, because anything within the 15 degrees of the poles is distorted. So that's a problem. So we created our own projection method that's tangent, that essentially has no distortion wherever you sort of look. And so that's particularly helpful for Earth data sets if you're trying to look at what's happening climate-wise on the Earth. I mean, you saw a little bit of Earth in one of the tours. I mean, you can essentially create a tour of any data set that's in this environment. So it's quite flexible. And I didn't show you the tour that was done by a 6-year-old. There's a great tour done by a 16-year-old girl who did a tour about extrasolar planets, which is particularly relevant. And she really does a really fantastic tour about that.
Okay. Help me thank Curtis, please. Thank you.
Thank you.
Thank you very much. So our second speaker for, wow, time to dance.
Sorry.
Our second speaker for this session is Tim Smith from CERN. And of course, I think everyone knows what CERN is. The anglicized spelling of that acronym is the European Organization for Nuclear Research. And Tim has been so gracious to appear before IXTE venues before. He's active in this area as well. He holds a PhD in physics and performed research at the CERN LEP Accelerator for 10 years before moving to IT. He leads a group in the CERN IT department that provides services for the 10,000-strong CERN user community, covering the domains of audiovisual, conferencing, document management, print shop, and copy editing, as well as the IT help desk. Of course, these responsibilities cover the burgeoning area of multimedia, and Tim oversees CERN's multimedia archive, which contains 25 terabytes of open access photos and videos. In addition to the technology of disseminating multimedia, he will also give us a view of how scientists at CERN are capturing their work in the form of visual media. Help me welcome Tim Smith. Thank you.
Okay, I'll go anyway. So thanks very much for inviting me here to speak. What I'm going to talk about is, in fact, the work of many other people, so I'd like to first of all acknowledge that it's the physicists around the world who work for CERN, at CERN, with CERN, that I'm going to present their work here. Now, multimedia means so many different things. Yep. I can move it up if you can't hear. Yeah, the scope of multimedia has expanded so much over recent years that it covers so many different diverse things that instead of going into any one in particular, I'm going to go and skim across the top. So I hope it isn't too light for you. But I'm going to start with talking about how multimedia is used in communications to the public, which in general is slightly different in the way that we use the multimedia for the scientists themselves. But when I get onto that, I'll talk just a tiny little bit on the supporting technologies behind that. So starting with the public and starting with the weird and wonderful, physicists around the world come up with different ways to engage the public and try and make what they're doing inside the buildings interesting to the public walking outside. So here is one idea from the Danish physicists who projected with 96 LED projectors onto their physics institute real-time events as they were happening in the collider. The tracks go across their institute just to try and attract the attention of people walking by and get them to come in and ask what on earth this is all about. That's called the kaleidoscope. A group in London took the reconstruction event, the reconstructed events, so rather than the raw data, take the tracks and the identified particles and fed it through music composition software that generated music from the events. So this way you can not only hear about the Higgs particle when we find it, but you can hear the Higgs particle.
What's it going to sound like?
And then how do you attract the younger generation? Well, gaming is the only way to attract them. So what we did was we made a little CERNland game. You can't actually see this very well. Can I dim? Here we go. So the idea here being to try and attract their attention by making it a game, but nonetheless have all the correct elements of quarks and gluons and how to construct protons and neutrons out of their elements so that they sort of absorb the physics and perhaps get fascinated by it just by playing around with it. But once we've got the attention of the public, they obviously want more information. They want to explore what we're doing. It's in recent years we've been called the cathedrals of science, and you want to walk around the cathedral. But the problem is that it's 100 meters underground, and not only is it underground and it's in a big cavern, but the experiment itself is massive and completely fills the cavern. So even if you get to go down there, which is unfortunately extremely rare chance, you can hardly get a perspective of the whole thing, and you can only go on a tiny little tour of it. So what we wanted to do was give them some way of exploring it without having to go down. And the solution was, we painted it on the outside of the buildings. No, actually, that's not what we did, but well, it is what we did, but it's not the solution. So we painted it real scale so that we could actually give an impression for the people that came to visit and can't actually go down. But what we did was we started to create a virtual tour, an interactive video, so you could actually explore it without actually going down. So what we did here is we made a navigation graph of the entire cavern where you can walk on the passerelles and the walkways, where the viewing points might be useful from. And then we we got some experts to come in and take 360-degree pan photography at each of these intersection points on the graph. We coded all this up in Flash, and then we also, between all the connector points, we made videos so that we could put all this together into a virtual tour. So again, it doesn't show very well. So I'll risk doing this online. So here is the result. This means that you can now, at any given point, you can start rotating around, zooming in, zooming out, the normal way of a sort of a tour. And then if you go round to the edge and then you start saying, oh, I want to walk along there, then it actually goes and walks you along the video, along the connectors, to the next point. And then when you've got a decision point, then you can interact with the Flash, which has put it all together. So at this point here, I walked into the lift, and I can choose which floor I want to go on, and then I'll come out on the somewhere else. So this gives people who can't go down at least an impression of what it's all about. And once they've got an impression, they want to know more about it. What are these experiments? What are what's going on in the apparatus? So what we try and do here is we make illustrative videos. So the top right-hand corner there is an illustration of the experimental apparatus itself. I think perhaps I'll just leave the lights down because these are all rather dark. So what we have here is we've coded into just an animation software the outer shells of the apparatus, and then we do a cutaway so that we can go in. So if only I'd known about the software that was described by this morning, well, I'd have done this differently. But it cuts away, and then you can see what's actually happening in the heart of the experiment. And underneath, you can also show by analogy what a magnetic trap looks like by portraying it as a sort of a hill in terms of a gravitational analogy. Other things that we can do with the illustrative videos are explain how the accelerator themselves work, how we collect particles, how the electric and magnetic fields work. So these are very useful tools, but they have their limitations. So when we get on to explaining the processes that are under study, in this case here, this was an anti-hydrogen trap, and what happens is when the anti-hydrogen finally leaves the trap and hits the outer wall, it annihilates, and you see the decay products. So this is fine for a relatively simple experiment like this. You can recode it up into an animation software and get something useful for the public. But when it comes to the bigger experiments, when there are millions of detector elements and tens of thousands of tracks coming out, we don't want to go and code all that in just for the sake of illustration. So instead, we have to have a different approach, and there we start from what the physicists themselves use. So the physicist himself wants an accurate representation so he can visualize what's happening in each of the events. So for any given event, we have a reconstruction software that takes the 100 million channels of readout and allows you to visualize it in various different ways. You can actually, the reconstruction program itself joins all the dots to make tracks and shows you where the energy depositions are. So you can actually see what's happening in the event in the center, and the physicist can then rotate it around in 3D, take slices through it, or make projections, so energy projection plots on theta phi or theta eta plots. So this is what the physicist wants, and is a very powerful tool, but nonetheless, this doesn't actually convey enough information to a non-expert. It's actually coded in, the whole reconstruction is coded in C++, so we have converters to make these event displays work that actually extract the information into XML, which then a Java visualizer can actually work on. Now that intermediate step, the XML, we can use to feed into the other software, some visualization software, and make it useful for or understandable for the public. So the usual stuff that goes on in something like 3D Studio Max, when you convert, you you then smooth, you add texture, and then we can basically make a video replay of the event as it happened in slowed down, so we can explain to the public what's actually happening in the center there. Let me just get rid of the... So here, pointing to our digital library, here is the video that comes out of this. So this is taken from real data, a real collision. We haven't had to code it back in. We've just converted the information into something that the renderer can actually work on there. So you can see the collision and the particles coming out. Sorry, this is real time from CERN over wireless, so I'm asking a bit much. And then you can see the energy depositions in the calorimeters from the outside, and then we just rotate it round. So this has the limitations of video that were just mentioned, but nonetheless, it allows us to explain our science a lot easier than using one of the complex programs that the physicists themselves use. So once we've explained what's going on in the apparatus, the next thing that we want to do to get them to understand is the theories that go behind. What are we trying to study and why? And that's a lot more challenging for us to try and explain some of these concepts that the theorists are coming up with. Hidden dimensions, parallel universes, strings. I put antimatter there because most people think it's a theory rather than something that we actually create and use in the lab. So what we happily rely on here is the creative genius of authors around the world, like Philip Pullman and Dan Brown here, and Hollywood to explain exactly what these theories are all about. So the relevance here is that when we discussed this with Sony Entertainment, they agreed that we could, if they were allowed to film in our underground chambers, then we could put our multimedia material along with the video. So actually, if you look at the Blu-ray disc of the Angels and Demons, you've got the whole multimedia pack from CERN explaining what is, in fact, the science behind Angels and Demons. So they created our own special ambigram for that. So that's great. We got the attention of the public, but of course, these authors don't always portray it in the best light. So it creates a lot of fear as well. So people were worried whether or not we were actually creating Earth-eating black holes. So we had to work out a way of actually allaying their fears and giving them sufficient information. So what we decided was the best way to do science is really to do it open with everyone watching at the time we do it. So when we were switching on, we decided to open up the lab and have a webcast so people could really see what we were doing, and they could have links to all the supplementary material at the same time. So this worked extremely well. The public were interested, and we got 1 million watchers of the webcast, which seems to have been the biggest scientific webcast to date. And at that time, when they started hitting our network, they were asking for more and more multimedia material for these explanations and things like that. So that put a huge stress on the infrastructure underneath, because they want from one place to start navigating out to all the extra information, exactly what we were talking about, these extended publications. They want to go through our entire digital library, especially the multimedia part of it. So this, that was the webcast itself. This put enormous challenges on our digital library. So just another side of multimedia is how you serve it to the outside world. So prior to the multimedia library, we just had basically one instance of this is the CERN Digital Library, CDS, which, okay, it was a front-end, back-end, but it was just one simple item. So when multimedia comes into the game, unfortunately, then you have to have streaming servers that can stream the content. You have to have transcoders that can translate it into all sorts of different formats that the different browsers and different usage patterns want to use. You have to have servers that can serve it securely for the high-resolution ones that can orchestrate this whole thing, and not just a few, but many, many, many. So we turned in from one server into a farm of 30 or 40 servers just to serve multimedia content. So the flip side of having having interest and having content is you have to manage it in a completely different way. So given the location we're in, I just wanted to point out that we achieve all this by actually using virtualization, and these are all based on Hyper-V virtualization machines. We can just instantiate them as needed if there's more transcoding or more streaming needing to be done underneath there. So what do the physicists want, sort of going from the public side? The physicists want a similar thing. They also want to see streaming media, but they want to see it from internally on site. They want to see at any given time what's happening in all the other lecture theatres, and they don't want to be sitting in front of all of them. So we've set up this this system whereby basically any lecture anywhere on site can be streamed to through the webcast server. Just a comment here, we find that rather than just filming one part of it, I think it was John was showing this yesterday as well, what our scientists want is that, in fact, to see exactly what's being pointed at, so we capture the VGA, and they don't particularly want to see what the lecturer is waving his hands at, especially when it happens to be in a darkened room and you can't see anything, so hence the relative sizes. But once they've watched it live, they want to go back and either download it or jump to somewhere and look at something specific in there. So what they want from the same webcast is afterwards to have a web lecture which they can then use and jump around in. So to be able to do this, we capture the video, the audio, the VGA signal, even the whiteboards the theorists still use. And we try and put that together into a lecture object. We analyze it, again, like was described yesterday, so that we can detect all the slide transitions, and we can make chapters. We can make it into an interesting blob for the scientists to use. So this is what it then looks like, is they can download this, they can use it, they can see it on the web. This is a big flash object where you can jump forwards, next slide, back slide, and you can see the slides and the speaker. Or you can jump anywhere in it because we've done the slide transitions. You can jump along, and you can just look at any, and the video syncs off, and you can just look at what the lecturer is saying at any given point. So this is one type of multimedia, the stuff that's more like what the public are after. But the other side of it, which was discussed this morning, I think, by Michael, was that they want all sorts of other information which is vaguely classed as multimedia information, which supports the science that's going on. So along with the publication, they want the data sets, they want the supplementary plots, any things that didn't actually make the publication but support it. They want access to all of this stuff. And of course, in a linked way also to the presentations and videos that I said. So this means that in our digital library, starting getting more and more little tabs coming along here with the extra pieces of information that they want. And as was mentioned this morning, they want to be able to add their data set there such that someone else can analyze it. So you can click on the data set and it will bring up the analysis program that all the physicists use, load up the data, and then just allow you to revalidate what was being discussed in the paper. Now, one little aspect I'd like to bring up here that wasn't mentioned this morning is this is all great as a new tool for new people that are thinking of new ways of using it. But to attract the people who have one way of doing things, that are used to things, we have to actually show them that it's useful. And there's this sort of chicken and egg that if they're the first one to put it in and they're not seeing anyone else using it, then they don't really want to put it in and be the first. So rather than looking at just stuff that's being contributed, we decided to go a different way through it and see what we could mine out and put in there anyway to show the value of having it there in the first place. So just take a couple of slides on that. So the first thing that we tried to do was to mine out all of the plots. So from the zip files that are contributed, or the PDFs, or even the raw tech files, we go through with analysis programs, start extracting all the information and putting them out as separate objects behind all of the publications automatically. So this already was started to be extremely useful, because then the physicists see that they don't have to measure things on paper anymore. They can get to the original objects. But then what we did was we started extracting the captions as well, which means that this is much more useful information, because then you can start doing searches on it search on the full text with a caption on this, with a plot that discussed a certain particular particle. And you can really hone down in very quickly on the graphs that you're interested in. But this takes quite a lot of processing power. So the next logical step from that was, once you've got objects like this, which are not textual, you want to do searching not just in the classic way on the caption, but actually on the image itself. So there we started working with the University of Geneva on some of the tools that they were doing for medical imaging. And we started to see whether this could actually be useful in our domain, whether or not you can use these tools which actually look for the color distributions and the different shapes and surfaces, and can actually go through our data with any use. So this was from the lab. This is not in production yet, but it allowed you just to click, I want something similar to this or not like that, and then it would do a search through the entire multimedia database based on this the tool having already indexed all these features. So another thing I think I've shown you sometime in the past already, another way of visualizing things. This is done already in many different ways, but it's very fun. Once we're starting to analyze all the papers, the tech and the PDFs and things, you can extract all sorts of different pieces of information out from them automatically. So here we've extracted all the references. Then we do the citation graph, the citation network, and the co-citation network, and then we can start plotting things that visually speak a lot quicker to people. So, for instance, a new person, a new researcher can see that this was a very hot topic in the 1970s here, and didn't die off. Some papers lose their interest completely. The subject's no longer interesting. This is obviously a really seminal work because it stood the test of time. And they can look for just shapes in the plots here, like this one. It's obviously something that's really hot. It's taking off, and it allows the young researcher to focus more on the type of articles they're interested in, because you can search for things that were interesting, are interesting, are taking off, and things like that, just by the shapes that you can see through these visual patterns. I won't talk much on the tag crowds and other things that are normal now in the social tools, trying to bring them back to the science community as well. So all of this, of course, needs a lot of analysis power. So what we have to do, instead of just having a digital library, the digital library now has to be able to dispatch all of these tasks for mining off. So we parallelize it, dispatch it, and then collect and reintegrate the results, often indexed results with the indexing from the classic text indexing. So we did this on the grid originally. We made connectors out to our grid that the physicists use for the analysis, and are now doing it actually out into the cloud instead. I won't talk about all the other things because I probably haven't got time. So just on to more things to do with visualization. Something we tried 10 years ago was to see what virtual reality could do for us to help with the assembly. So the LHC was constructed by institutes around the world, and they had to validate that what was being made in these different places would actually fit together. And it's a sort of 27-kilometer long accelerator, so it was quite a challenge. There were 142 different CAD systems being used around the world, and they had to integrate the information together in order to validate it. So what they did was they made a virtual reality lab. This is 10 years ago, so these were massive goggles with your hands on balls, and you could navigate through and just see whether or not a cooling pipe would go through an electrical supply or something like that. So this was fun and useful, but you had to be at CERN in that virtual reality lab, so it didn't get much use. So when we came to describing or assembling the detectors later on, we tried another technique, which was something that anybody could view from anywhere, which was to take all the diagrams and to try and work through a time sequence of how we would actually put them together. And then we could just run it in front of people and see if that fitted what they thought they were going to be doing, what they were responsible for and to make sure that it works. So each of these are animation videos taken from the CAD output, again with the texturizing and the surface coloring and things like that. And then we just animate it with a timeline to make sure that things insert as they're inspected and there aren't any clashes. So this turned out to be quite a useful tool for the assembly and is useful afterwards for the public to understand what makes a detector and how does it go together. So one last visualization thing to do with the grid. So the physicists distribute the data all around to the participating institutes because we haven't got enough compute power or even data storage to have everything at CERN in multiple copies. So we distribute jobs around the world, dispatch them, then bring them back together, the results, across the grid. So we have a visualization tool that shows how these jobs and the data gets distributed to the 350 centers around the world that are actually participating in this grid. So just see if this works. So then you can see real time the distribution of jobs. It's just pulsating because to give a visual impact of how big each of the centers are. But you can see the data transfers and the job transfers meant to be real time around the grid. So that's about it for the summary of the different techniques that we use. So I just want to finish and ask if there's any questions.
John?
Tim, wearing a taxpayer's hat, as I understand it, the amount of running time for the LHC to prove the Higgs boson is a critical feature. How do you try and convey that you've not yet got statistical certainty on a particular particle? So if you combine the worldwide telescope type of approach, then you would have to have some slide bar for speeding up, showing accumulation of data, and that would, convey to the general public, that the machine needs to keep running until you prove it.
The way we generally do it is because it's a statistical analysis, and you have to show a signal over a massive background. We generally do it just by literally showing what we have accumulated to date in the distributions, and we just show that you can't possibly see anything with the statistical accuracy. And then with the modeling of the detector over 20 years, we can show how the error bars go down. The problem is all of this is statistical, and error bars and things like that, it's hard to convey that sort of stuff to the public.
Other questions? All right. Thank you very much, Tim.